Alright, so this video is going to be talking about vapor pressure. So a lot of times vapor pressure is demonstrated to you, or you're going to be like interpreting a graph like shown here. So vapor pressure in general, I'm just going to draw a little picture here. Say we have a container of a liquid, for example water. They're all the little liquid water molecules, right? As those the vapor pressure is the pressure of the vapor above the liquid. See, some of those liquid molecules might go into the gas phase in a closed container. So this is a closed system. So if this was water, enough of the molecules on the surface of it get enough kinetic energy that those are arrows, that go into the gas phase, and they now create a pressure by running into each other and the sides of the container. So the point of this today is to talk about the relationship between IMFs and vapor pressure. Now, looking at this graph, you can see that in general, as this graph is on vapor pressure versus temperature, in general, as temperature is increasing, the vapor pressure is increasing. This is because the more temperature that something has, the more kinetic energy the molecules will have, so more will go into the gas phase. But we're going to look at each substance individually and look at how their vapor pressures compare. So we have water, ethyl alcohol, or ethanol, and this is diethyl ether. Now you don't need to draw these structures, but understand that this right here, it's really a C2H5. Now, this is not drawn properly, but then there's an oxygen and another C2H5. So this guy is nonpolar, which I drew an ether in a previous lecture. But that guy's nonpolar, so really the only force that this guy's going to have is London dispersion forces. Ethanol is polar, as is water, and both of them have hydrogen bonding. So looking at the diethyl ether, so this guy, since he is London dispersion forces, he has weak intermolecular forces. This is going to cause little attraction between the liquid molecules, and so therefore more of them will go into the gas phase at any particular temperature. So its vapor pressure is they're going to have more vapor at any given temperature. So if we were to look at these three substances at a particular temperature, like say here, all three of these substances have a vapor pressure value at that given temperature of about 30 degrees Celsius. So if we were to look at these, which one has the most vapor pressure? Oh, it's the diethyl ether, the one that has London dispersion forces. All right. So, but then if we were to look at the other two, why would ethanol have a slightly higher vapor pressure than just water? They're both hydrogen bonding, but remember water looks like this. Ethanol only has that one OH group. So ethanol only has one site for hydrogen bonding, while water has two. So since there's two sites, it's a stronger hydrogen bond. So that's why its vapor pressure is even lower than ethanol. Right? So if we were to make a general statement about vapor pressure, we would say that, and relating to IMFs, we would say that the stronger the IMF, the lower the vapor pressure. And that's something that you need to understand, and we're going to be talking about today with regards to many different examples and explaining why. Alright, so let's look at this here. If I were to take some water and throw it in a closed container, I'm using water, any liquid. Water is the most common example. Initially, all I have is liquid water in here, right? There's no gas. So at first, the reaction of, we have a liquid, some of it's going to go to the gas phase, so it's going to be this type of equation where you have liquid going to the gas phase, because some of that water is going to evaporate because it wants to create some vapor pressure. It doesn't want to all stay in the liquid phase. Some of it will get enough kinetic energy to go to the gas phase. So at first, this proceeds in a forward direction because we have no gas. It needs to create some. This will occur until the energy levels out, and then we reach equilibrium where we have H2O liquid. It's in equilibrium with H2O gas. And we're going to spend like 3 units on equilibrium and going into great detail, but you should be familiar with the concept. So equilibrium happens when for every one water molecule or liquid molecule that is going to the gas phase, you have one that's coming back to the liquid phase. So there's no net change in the number of gas molecules or the number of liquid molecules. All right. So this leads us into our more advanced this leads us into a definition of vapor pressure different from what we said before, because it's the pressure at equilibrium. That was not something I mentioned back here when we talked about this, but this only occurs, you can only measure the vapor pressure once it's at equilibrium. So vapor pressure is the pressure of the vapor present at equilibrium. And a system at equilibrium is when no net change occurs in the amount of liquid or vapor because they're balancing each other out. So here is an interesting question. You have to think it through. So what is the vapor pressure of water at 100 degrees Celsius? Or we could say, what is this vapor pressure equal to? So let's think about what happens at 100 degrees Celsius. Well, at 100 degrees Celsius, this is of water, water is boiling. It boils. So you have a container. We're going to leave this one open. It's not going to be a closed container. You have the liquid. You have liquid molecules going to the gas phase. All right. When it's boiling at 100 degrees Celsius, it's not all, they're not all going to the gas phase. It's just it's at that point where water molecules are going to the gas phase, and some are going back down to the liquid phase because it's at only 100 degrees Celsius. All right. So there's a pressure pushing down on this as well. That pressure pushing down is equal to the pressure that the liquid molecules, as they go to the gas phase, is pushing up. Right? At phase changes, boiling, melting, freezing, condensing, all those things. At phase changes, you have equal pressure going up and coming down. Not really with freezing and melting just because that's solid and stuff like that, but it's at equilibrium. You have equal transitions from the liquid to the gas and the gas to the liquid at those phase changes. If you want it to be more on the gas side, you'd have to increase the temperature above 100 degrees Celsius. So at 100 degrees Celsius, there is an equilibrium between the pressure pushing down and the pressure pushing up. Well, this pressure pushing down, if it's open, it's coming from the atmosphere. All right. So the vapor pressure of water is the atmospheric pressure. All right. And so one thing I want to say as well is, so boiling point, this is what I was saying before, boiling point is when the atmospheric pressure is equal to the vapor pressure. Okay, that's a more advanced definition of boiling point. It's not just the temperature at which something boils. It actually is when that atmospheric pressure and the vapor pressure are equal. So whatever the atmospheric pressure is, that's what the vapor pressure is if the substance is at the boiling point. Now, typically, the vapor pressure is at standard 1 atmosphere. You might also see this as written as the normal pressure. So normal pressure, standard pressure, same thing. All right, so here we have an old-fashioned barometer. The silver colored stuff, that's mercury. So this is how they used to find vapor pressure and barometric pressure. So looking at this first one, we have just mercury in a tube. It was inverted into a little dish that had more mercury. The only thing pushing down on this is the atmosphere, and after it levels out, it creates a vacuum, because that's the only thing that was in there, and this height here, that height was 760 millimeters, and it was of mercury, and that's where they got 760 torr. But we can use barometers to find vapor pressure of different substances. So looking at the other three, those are the exact same substances that we plotted before, or that we looked at being plotted on the very first little bit of this. So, for example, if we have water vapor in there, after it reaches equilibrium, water vapor's in there, and now we have two competing pressures. We have the pressure of the water vapor pushing down on the mercury in the tube, and we have the atmospheric pressure pushing down on the mercury in the tub. Where they kind of balance out, that tells us the vapor pressure of water. And so you take what initially was the standard pressure, which was 760, and you subtract what that height is now, 736, and you get that the vapor pressure of water is 24 torr. Right? We could do this with each one. So looking at the next one, again, same thing. We have the competing vapor pressures. This one has a slightly higher vapor pressure, remember, because one less hydrogen bond available. So it's going to have a slightly higher one, but the process is the same. Take 760 minus 695, which is this height, and you get the vapor pressure of the ethanol. Now, the diethyl ether has a really, really, really high vapor pressure because it has a weak intermolecular force. It's only London dispersion forces. So this distance here, not this distance, eraser. There we go. So this distance here is only 215. And so when they subtract that from 760, you get 554. Okay, which should be this distance. All right, so this is the exact same graph that we saw before. It's just prettier and in color. So we could compare, the three substances at a given temperature. All right, so I could see them asking lots of different questions about this one graph, so don't be scared of it. Just learn how to read it and learn how to understand how ones with large intermolecular forces have low vapor pressures and why and all that stuff. All right, so moving on, introducing the Clausius-Clapeyron equation. You do not need to memorize this. All right, but this will allow us to determine the enthalpy of vaporization, which is delta H vap. So this is the heat required to vaporize a substance. Vaporize or boil a substance. Boil. All right, so with this, you would need to know two sets of like ordered pairs type thing. You would need to know the vapor pressure, which is PVAP, of one temperature and that temperature, and you would need to know the vapor pressure of a second temperature and that temperature. So you need two different sets of pairs. The R that's in this is the R for energy, that one, which is on your formula sheet, don't need to memorize, and temperature, as always, with calculations, almost always with calculations, is going to be in Kelvin. So for this, we could find what the delta H vaporization is, or maybe, which the example problem we're going to do, it gives you the delta H vaporization, and we're finding what the other vapor pressure is. So let's go ahead and do that problem. So here we have that the vapor pressure of water at 25 degrees Celsius, so that's something important, 25 degrees Celsius, that's our T1, is 23.8 torr. So 23.8 torr is I'm just going to leave it as P1 instead of P vape 1. So that's our first pressure. And then we want to know what is the vapor pressure at 65 degrees Celsius. So that's going to be T2, and I don't know P2. But this isn't just this isn't a gas law where we can just do P1 over T1, because first of all, it's vapor pressure, not pressure of a certain gas. There's a difference, and I mean that's the main difference. So we also know that delta H is, as I'm writing with my hand accidentally, delta H is 43.9 kilojoules per mole. And again, R is the 8.314 joules per Kelvin mole. All right. So, I just realized I've run out of room, so hold on a second. All right, so I had to duplicate the page. It took me a moment to do that. All right, so if we were to set this up, I'm going to go on to the next page. We're going to lose all the givens, but you can always pause and go back to it. So if we were to set up the problem, the Clausius-Clapeyron equation, which is on two slides back, also in your notes that you should be following along with, we're going to take the natural log of the first pressure, P1, which is 23.8, over, we don't know P2, and that equals the delta H over R. Well, delta H, I'm going to go back, delta H was given to us in kilojoules per mole, but R is in joules, so we need to get them both to the same thing. It's easier to convert, it's easier just to convert the delta H, so 43.9 kilojoules per mole is 43900 joules per mole, and that's over R, which is the 8.314 joules per Kelvin mole. And then this is multiplied by the 1 over the temperatures. So the first time, no, it's T2 minus T1. So T2 is 65 degrees Celsius, which is 65 plus 273, probably should have had this done already, is 338 Kelvin. And then we're going to subtract 1 over T1, which is 298 Kelvin. So now, you can do some of the math here, like everything on the right you can go ahead and do, which you, when you do all that math, we're just going to label it as X. Because in order to cancel out the natural log, the opposite of natural log is e to the something, to whatever that is. And an easy way to remember that is you look at the second function on your calculator. Natural log is ln. The second function is e to the x. So we have to do e to both sides. So on the left, we're going to take e to the natural log of 23.8 over p2 equals e to the x. And x is whatever this ends up being. That's x. So when you take e to the natural log of something, it cancels that out completely. So this goes away. So then you just get 23.8 over p2 equals e to the x. Right? And when you do that math, you should get p2 is 193.7 torr. Alright, so the last thing is looking at a heating curve, which you should be somewhat familiar with. So yours is not in color on your page, but here it is. This purple part is when it's solid. The green part is where it's liquid, and the red part is where it's a gas. The straight, the horizontal lines in between those are going to be your phase changes. So here is our where the ice would melt to make water, or if you were taking away energy, the water would freeze to make ice. So another name for melting is fusion. So delta H fusion, my pen is messing up. Delta H fusion. Seriously? It's like me with the Promethean board sometimes. There we go. So delta H fusion, And then this is our delta H of vaporization, the orange part. Okay, so the question is, which would we predict to be larger for a given substance, our delta H vaporization or delta H fusion? So just looking at it, something boils for a lot longer than something melts for. So the energy here is larger, and the reason why is, think about it, like when you're going from a solid to a liquid, yeah, you're overcoming some of those intermolecular forces, but they're still attracted to each other. They're still close together. They're not as close as they were in the solid form, but they're still pretty close. When you go from a liquid to a gas, you have to overcome all the IMFs. Because those molecules are even more spread apart, like there's barely any attraction. So you have to add so much energy that they overcome all of their intermolecular forces. So the answer would be delta H vaporization, and the reason why is what we just said. All right, so that concludes vapor pressure. So any questions you have, bring them the next time I see you. Attempt the homework, follow along with your book. We'll do more practice problems with this and everything else we've learned up until this point. Okay? I'll see you when I see you.